Okay, howdy folks. Vertical stretch on sinusoidal graph. So let's continue our exploration here. Let's graph a bunch of these. This time the cosine function. Okay, so first off, what I'm going to do is I'm going to graph the cosine function. We haven't graphed that yet. So off to the right, I've given you a table of values. Okay, do the same sort of thing we did with the sine function, but now with cosine. So when x is 0, cosine is 1. When x is pi over 6, cosine is pi over 3 divided by 2. That's roughly 0.87. That'll help you graph it, okay? And then so on. So you know how to derive all these values. 1/2, 0, negative 1/2, negative square root of 3 over 2. That's about negative 0.87. Okay, negative 1, negative square root of 3 over 2. That's about negative 0.87. Okay, 4 pi over 3, that's about negative 1/2. 3 pi over 2 is 0. Okay, and so on. Let me fill in the rest of these. It's 1/2 square root of 3 over 2. Okay, and then 2 pi is just 1. Okay, when I throw these on the graph, I have 0, 1. So there we go. Pi over 6. So each tick mark is pi over 6, right? So this is pi over 2, which is the same as 3 pi over 6. So every tick mark here is pi over 6. Okay? 2 pi over 6. 3 pi over 6. Okay, so remember that. That's one of the trickier things about using radians, is that we have to keep those kind of units straight. Okay, so pi over 6, 0.87. Right about there. Pi over 3, 1/2. Pi over 2, 0. 2 pi over 3, negative 1/2. Okay, 5 pi over 6, negative 0.87. And then pi is negative 1. So you see a pattern here. I'm just going to use symmetry. We know what these are going to look like. Right? So there's our pattern. Okay, so I'm going to connect the dots here. Okay. And then, just for fun, I'm going to continue that on through, right? Because I know what it's going to look like. Just all the way through, right? With a nice long cosine graph. Okay. Okay, let's build our next one, which is, it says on the graph below, sketch y equals cosine of x for the domain 0, x is greater than or equal to 0, less than or equal to 2 pi. I've done that and then just stretched it out a little bit more. Want a nice long graph to see what it looks like. In red, I'm going to show you y equals 3 cosine of x. Okay, so that's the a value. So let's go back up here, right? Transformation to what is this a value? This is the a value. This is the same a value we've been dealing with function transformations. When we multiply a function by a and it's a positive value and it increases like from 1 to 2 to 3, what does it do? It vertically stretches it out. So it makes it like taller, right? So it vertically stretches it out. So instead of 1 unit, if I stretch it by an a value of 3, then it's going to go to 3. So 1, 2, 3. So every point, every y value on the y equals cosine of x graph gets multiplied by 3. And you can see that mathematically right here. Right? So if I take the cosine function and multiply it by 3, all the y values will get multiplied by 3. So this one, when I multiply by 3, goes all the way up here, about there. and then 1/2 multiplied by 3, 1, 2, 3, right about there. And then 0 multiplied by 3 is just still there, okay? And then so on. So we're going to have some symmetry here. So right about there. 1, 2, 3, 1, 2, 3. Okay, and then so on, right? So I'm going to plot all these points. There, 1, 2, 3. Okay, and then let's keep going. Let's just finish this all the way out. Okay. And they're going to have this nice looking sinusoidal curve here. Okay. So in red, that is y equals 3 cosine of x. Okay. And then I should say in black here, let me just so I can get all the colors correct. In black, it's y equals cosine of x. Okay. Let's look at y equals 1/3 cosine of x, which is in blue. I'll make that in blue. Well, when it's 1/3, what should we expect? Right here. This is an a value of 1/3. Previously, this was an a value of 3. So what should we expect when we multiply by an a value of 1/3? It should shrink all the y coordinates, or the y values of the original graph, y equals cosine of x, by a factor of 1/3. So let's show that physically on the graph. So 1/3, right about there. 1/3. Oops. Okay, this is going to be a very, very shallow, like, graph. Oops. Right about there. Okay, you get the idea, and so on, right? So I'm looking at 1/3 of the original cosine graph as I track it along here, 1/3 roughly. Okay, and then so it looks like this, folks. It looks like it's been smushed down a little bit, right? Okay. All right, and then the last one I'll do in green. What do we expect from that, right? So we have in green, this is an a value of -2. Okay, a value of -2. Well, there's going to be a reflection because a is less than 0, and there's going to be a vertical stretch about the x-axis, right? So we can do it two ways. We can double all the y coordinates, double all the y values of the cosine. Well, let's do it this way. Double all the y values of the cosine, original cosine function, then just reflect it. So if I double it and reflect it, so here's the original cosine function. I double it and then reflect it down to -2. This one, I double it and then I reflect it down because it's a -2 value. Okay, this one, I double it and then I reflect it down. Invariant point. Okay, let's keep going. I double it and I reflect it. So double it and then I reflect it up. I double it and then I reflect it up, which would be right about there. I double it and I reflect it up, And then you get the idea, and we get some symmetry going on. And then let's plot the rest of these. Okay, so you get the idea here. Okay, and you can see how the reflection happens, right? So it's been reflected. Okay, let's write down some characteristics of each of these functions, okay? All right, the domain. So I know the domain we set just for the purpose of the graph is x is greater than or equal to 0, is less than or equal to 2 pi. But let's think of it in terms of a graph that continues on and on, right? So in fact, the domain of all of these are going to be negative to positive infinity, right? Because they just oscillate forever, right? Left and right. So all these domains are the same. Okay, what about the range? For y equals cosine of x, let's pay attention to this, right? The a value is 1, so the range, I'm going to use interval notation. It makes sense that the range is negative 1 to 1. For an a value of 3, a equals 3, well, that is negative 3 to positive 3. And that should make sense with our amplitude being equal to 3, right? We'll go over that amplitude and how it relates. An a value of 1/3, well, it makes sense that it's negative 1/3 to positive 1/3 for our interval or our range. And then an a value of negative 2, well, that's just negative 2 to positive 2. Maximum point 1, maximum point 3, maximum point 1/3, and maximum point 2. And that relates to the maximum point on all our ranges. What about our minimum? So it's just the negative value for the range. So negative 1 here, negative 3 here, negative 1/3 here, and negative 2 here. What about the period? Let's go back up here. When I look at the period, folks, on any of these, right? So I'll do the cosine one first. I start here. I need to complete one full cycle. That's half of an up cycle, one full down cycle, and then half of another up cycle. Well, I end up at 2 pi. So that's 2 pi is the period. Let's check another one. If I start with a red one, y equals 3 cosine of x, half of an up cycle, a full down cycle, and then a half of the other part of the up cycle, well, that's still 2 pi. Okay, what about the green one? Half of a down cycle here, full up cycle, and then half of the other down cycle. I stop, that's a full cycle. That's 2 pi right here. So still the same. Okay, what about the blue one? Half of it up cycle, full down cycle, and then the other half of the up cycle. I stop, it's 2 pi. So the period in all of these cases is all just 2 pi. Okay, amplitude. What do we define amplitude as? This is the last part. It is the maximum vertical distance the graph of a sinusoidal function that varies above and below the horizontal central axis of the curve. So let me just take the red curve here. This is y equals 3 cosine of x. If I start here, and I go down to the horizontal central axis of the curve, that is an amplitude of 3. From the negative side, I start here and I go to the horizontal central axis. that is also an amplitude of 3. Okay? Okay, let's go back to our graph here. So how does that relate to the other values here? So the amplitude is 3. Well, how does that, oh, sorry. This one on the y equals cosine of x, the amplitude is 1. Well, how does that relate to the other values? The amplitude, the maximum, the range, the a value. Okay? Amplitude, y equals 3 cosine of x, amplitude of 3. Amplitude of y equals 1/3 cosine of x, amplitude of 1/3. Amplitude of y equals -2 cosine of x. Well, this is, remember, amplitude a value is the absolute value, right? So a equals 1. Let's say the absolute value of a equals 1. Remember, that's how we determine our factor for a stretch. Absolute value of a equals 3. Absolute value of a equals 1/3. Absolute value of a equals 2, right? So that's how our amplitudes are related. So I'll highlight that to show you 3, 3. So the 1 and the 1 here, 3, 3. Maximum of 3. Max range of 3. A value of 3. A1, absolute value of A, 1/3. 1/3 for the amplitude. Maximum 1/3. High value on the range, 1/3. Absolute value of A, 1/3. Absolute value of A is 2. Amplitude of 2. Maximum of 2. Range. Maximum is 2. Absolute value of A is 2. Okay? Describe what characteristics are affected by the parameter A in the sinusoidal function. So A, oh, come on. So the A, okay, my pen is really slow. Sorry about that, folks. Let's just save it. Give me a sec here. Okay, let's try this again. Okay, the A value okay, this is really annoying. Sorry about that, folks. I'm gonna see if I can get this lag to disappear here. Okay, let me read it out. Describe what characteristics are affected by the parameter A in the sinusoidal function. So A affects the amplitude of the function by vertically stretching the graph about the x-axis, and that's what we saw in this series of graphs here, right? We saw the vertical stretch clearly happening, right, folks? So if we go up, we saw the vertical stretch happening in these graphs, right? So the A value affects the amplitude of the function by vertically stretching the graph about the x-axis. So this is really nothing new. We knew this from our transformations unit, right? We know the A value is a vertical stretch about the x-axis of whatever function you're dealing with. In this case, for a sinusoidal function, this is a cosine function or the sine function, it will affect what's called the amplitude. So we have to think in terms of new terminology because we're dealing with sinusoidal functions. We have to now start calling it the amplitude. Okay? So let's finish here. For y equals cosine of x, the absolute value of a equals 1, the amplitude is just 1. So if I take the maximum value, the amplitude 1, minus the minimum 1, divided by 2. So, sorry, maximum value 1 minus the minimum value, which is -1. So it's 1 minus -1, and I divide it by 2. I end up getting 1, which is the amplitude. For y equals 3 cosine of x, I take the absolute value of 3. The amplitude equals the maximum value, which is 3, minus the minimum, which is -3. So it's 3 minus -3 divided by 2 equals an amplitude of 3. For y equals -2 cosine of x, the absolute value of a is 2. So the amplitude equals the maximum value, which is 2, minus the minimum value, which is -2. So that's 2 minus -2 divided by 2. That equals 2. All right, folks, we are doing a vertical stretch on the graph y equals cosine of x. So if I show you y equals cosine of x, there it is. Okay, right now the a value is 1. So what happens when we apply a vertical stretch by a factor of 3? Vertical stretch about the x-axis. So we should expect the peaks to get higher and then the troughs or the minimums to get lower. So if I go 3, that's what we expect, right? So let's place that graph right here. Okay, and that's what we saw in class with our graph in red. So I'm going to turn this off. So that's where we are. Oh, let's turn it back on. Okay, and then the other graph we saw was y equals 1/3 cosine of x. So when we do 1/3 cosine of x, what should we expect? So let me take the black graph. Now if I go to 1/3 roughly, it's going to flatten out. That's what it looks like. So when we turn this on here, there's the blue graph. So let me turn the red one off. You can see that the blue graph, the peaks, look at them, pick any maximum, you'll see that it's 1/3 the value of the original y equals cosine of x. Okay, there we go. And then what's the last one? -2 cosine of x. So let's turn this off. And then let me go to, first of all, to 2. When I go to 2, I'm going to multiply all the y values by a factor of 2. So the peaks and the troughs are going to multiply by a factor of 2. So it'll get taller, right? So that you can see the peaks go up from 1 to 2. What happens when we go negative? Because the last one in green was y equals -2 cosine of x. Well, if I keep that there and then I put that here, well, it's just going to flip it over. So -2, it's going to be a reflection in the x-axis. So let's put all of that together. I'm going to go back to 1 here. So there's our original cosine graph, a value of 3, right? So it's a vertical stretch about the x-axis. A value of 1/3, it's a vertical stretch about the x-axis by a factor of 1/3. And then a value of -2, it's going to be a reflection and a vertical stretch by about the x-axis by a factor of 2. And there it is, just like in class. Hello everyone. Let's continue with horizontal stretch on sinusoidal graphs. So any function of the form y equals f of bx. So pay careful attention where that b value is related to y equals f of x by a horizontal stretch factor of 1 over b. We know this from our transformations unit. Absolute value of 1 over b about the y-axis, including the sine and cosine functions. If b is less than 0, then guess what happens? It's also reflected in the y-axis. Again, nothing new from our transformations unit. Okay, exploration, horizontal stretch on y equals sine of x. On the grid below, sketch y equals sine of x for 0, x is greater than or equal to 0, is less than or equal to 4. Okay, so for our sine values, I'll do sine of x in black. Okay, so this is our classic sine function here. So at x equals 0, sine is 0. At x equals pi over 6, sine is 1/2. Pi over 3, that's square root of 3 over 2. Pi over 2, that's 1. 2 pi over 3, that's square root of 3 over 2. Pi over 6, that's 1/2. At pi, it is back to 0. 7 pi over 6, that's -1/2. 4 pi over 3, -3 pi over 2. At 3 pi over 2, -1. At 5 pi over 3, negative square root of 3 over 2. At 11 pi over 6, that's -1/2. And then at 2 pi, that is 0. Okay, let's graph this, see what it looks like. Got 0, pi over 6, 1/2. Okay, pi over 3, square root of 3 over 2. At pi over 2, 1. At 2 pi over 3, square root of 3 over 2. And then at 5 pi over 6, 1/2, and then back down to pi at 0, then you'll see that the values are going to repeat like symmetrically here. So I know how to draw this going all the way through. Okay, so there we go, folks, all the way to 4 pi. So nice and smooth. Okay, that is y equals sine of x. On the same grid, how many periods are you graphing? So I'm graphing, I'll start here. That's 1 cycle, so that's 1 period, and that's 2 periods. So I'm graphing 2 periods as shown on my graph here. Okay, so let's fill that in. 2 periods. Okay, let's pick red. I'm going to graph y equals 1/2 sine of x. What do we predict will happen? Okay, let's see here. On the same grid, sketch y equals sine of 1/2 x. So let's do that right here. Okay, that means the amplitude doesn't change, but 1/2 x, if I do the factor, right? So if I say the factor 1 over absolute value of b, so that's 1 over 1/2, and that's a factor of 2. So everything from the sine x graph, so y equals sine of x graph, all the x values will be multiplied by 2. Okay, so I start here, and then that's multiplied by 2. This one's multiplied by 2. Okay, this one's multiplied by 2. This one is multiplied by 2, so it's over here. This one is multiplied by 2, so it's over here. This one is multiplied by 2, so it will be over here. And then this one is multiplied by 2, so pi becomes pi over 2. So you'll see the first half. Okay, and then so on. So let's continue here. Oops. So this is how we'll end up here. Okay. And then let's graph. Let's pause here. For the red graph, does that make sense? So I have a b value 1/2 and a factor of 2. What was the period? What's the period of the sine function? So the period of the sine function is 2 pi, right? So the period of the sine function is 2 pi. Okay. What's the period of y equals 1/2 sine of x? Well, we multiply by a factor of 2, so therefore it must be 2 pi times 2, which is 4 pi. Is the period of the red graph y equals 1/2 sine of x 4 pi? Well, let's take a look. Highlight in green. One full cycle. Well, look where we stop. Bingo. Okay, 4 pi. And that makes sense based on what we know about calculating horizontal stretch and our b value. Okay, so I'll just write this again. Period of y equals 1/2 sine of x is 4 pi. Well, then what will we guess happens when we do the blue graph? Okay, we're taking, so the blue graph factor, so y equals sine of 3x, factor is equal to 1 over the absolute value of b, which is 1 over absolute value of 3, and that equals 1/3, right? So all the x values of the original sine graph, we're going to multiply by a factor of 1/3. So it's going to stretch it by a factor of 1/3 about the y-axis. So 1/3, here we go, right about there, right about there, right about there. It's going to be really tight, the graph here. Okay, right about there. Let's draw that first bit in. Okay, and then continuing on, right? So it's going to look like that. Okay, continuing. Okay. So does this make sense? Period of y equals 3 sine of x is, what do you predict? If it's a factor of 1/3, right? So in yellow highlighter, I've shown the period of y equals sine of, yellow highlighter. I've shown the period of y equals sine of x as 2 pi, right? So that's clearly 2 pi. Let's show in pink highlighter here, y equals sine of x is, what is it? So it's 1/3 of 2 pi. So it should be 2 pi times 3. So let me write that in before we continue. That's 2 pi times 1/3, which is 2 pi over 3. Well, let's see if that's the case. So I start here where the blue graph is. There's one cycle, and I'm going to stop right there. What is that? That is, so we need to be good at reading these graphs carefully. So right here, each tick mark is pi over 3, right? sorry, each tick mark is pi over 6. So pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. So 4 pi over 6, which is 2 pi over 3, which is my new period. Okay, so my period is 2 pi over 3, and there we go, 2 pi over 3. Okay, let's fill in some characteristics. Complete the characteristic chart for the functions you just graphed, where x is defined on the set of real numbers and is expressed in radians. Okay, so all real numbers. So this time, the domain, you can clearly see y equals sine of x. So in black, it's negative and positive infinity. Y equals 1/2 sine of x in red. That's negative infinity, positive infinity. Okay, and then y equals sine of 3x, negative infinity, positive infinity. What about the range? The range, okay, remember we affected the x values, right? Not the y values. So the range will not change. The range will stay the same, -1, 1. And it's the same for all because we did not affect anything with the y values, okay? What about the period? We showed you the period. Oops, sorry, I'm going to color code it, so let's stay consistent here. -1, 1, -1, 1. Okay, what about the period? Period, right, we can show as the formula. I know it's 1 over absolute value of b, but we can show it when it has to do with trigonometry and a sine or a cosine function. We modify it slightly by saying 2 pi over the absolute value of b. And in this case, it's 2 pi over the absolute value of 1, which is just 2 pi. Okay, what about the function y equals sine of 1/2 x? Well, same formula, 2 pi over absolute value of b. That's 2 pi over absolute value of b is 1/2, and that equals 4 pi. So this is the formula that we'll use to determine the period when we have a horizontal stretch, right? So the b value changes. Okay, and then lastly, 2 pi over absolute value of b, that's 2 pi over 3, and that's the new period, just like we showed you with the graphical way and now the algebraic way. What about the amplitude? The amplitude, 1, 1, 1. Remember, we're not changing any y values, okay? Describe what characteristics are affected by the parameter b in the sinusoidal function. So b affects the period of the function by horizontally stretching the graph about the y-axis. Okay, and that's it. So again, nothing new, right? What formula could you use to determine the period of any sine or cosine function without graphing? Use the formula to find the period of y equals sine of -1/3 x. Verify answer by graphing in your calculator. Okay, so period equals 2 pi over the absolute value of b, and it equals 2 pi over the absolute value of -1/3, because my b value equals -1/3, and then that equals 6 pi. Okay, so grab your graphing calculator. Okay, and then carefully when you do this on your graphing calculator, so make sure you're in radian mode. Okay, so I need to change mine. So we're going to graph this to verify this. Okay, radian mode. Okay, number one. And then graph y equals sine of negative 1/3 x. Okay. When we graph this, change your window settings. You're in radian mode. Okay, the x min. So your x values, x min should be, let's go 0. Y min, or sorry, x min is 0. X max, let's go all the way to 12 pi. So you can type in 12 pi directly. 12 pi. And then our scale should be pi divided by 6. So every pi over 6 radians or 30 degrees. Okay. Y values, I'm just going to keep it as negative 1.2, 1.2, and scale of 0.2. Okay, so go ahead and graph that. Okay, so what do I get? I'm going to sketch the graph here. Okay, it went all the way to 12 pi, so like this. So this is -1, this is 1, and then you can clearly see that our amplitude, sorry, not our amplitude, our period is 6 pi graphically, right? But we determined that from our algebraic knowledge of how do we modify the period. So on the same graph, on your graphing calculator, graph y equals sine of x. So when you graph that, graph y equals sine of 1/3 x. And you'll see that, so the graph in red, this is y equals 1/3, y equals sine of -1/3 x. Okay, so that's the graph in red. And then let's graph y equals sine of x. Y equals, sine of 1/3 x. Okay, and let's adjust our window. Let's go x minimum -2 pi. Or actually, let's go window -6 pi so you can see maybe the full scale here. So just a second here. So you're going to see a graph that continues on like this, right? And think about, is it a graph that reflects, right? Is it a graph that reflects? Oh man. Is it a graph that reflects in the y-axis? Remember, this is the y-axis here. So if you turn this blue graph, if you reflect it across the y-axis, you'll see that it neatly overlays into the red axis and vice versa because they're reflections of each other. Okay, so if I highlight this portion, here's the red graph. And if you think about the red graph, and then if I think about the blue graph as reflected, does it look like it's a reflection about the y-axis? I think it does, right? If you take this as a pivot point right on the origin, and if you flip that yellow graph about the y-axis, you'll see that it neatly overlays on the pink graph. Just stop and pause and carefully look at that, okay? Hello everyone. We're doing a horizontal stretch on y equals sine of x. So there's our standard y equals sine of x. So the first graph in red, like we saw in the class example, y equals sine of 1/2 x. Well, the b value is 1/2. What happens when the b value is 1/2? What happens to the period? So in this sine y equals sine of x graph, the period is 2 pi. So if we have a b value of 1/2, that's 2 pi divided by 1/2, we're going to have a period of 4 pi, right? Remember that calculation? So it's going to be 4 pi. So if I go 1/2 here, we're going to expect the period to be larger, right? So it's like you're stretching out a spring. You're stretching it out, making it longer. The amplitude is going to stay the same because the b value does not affect any y values, right? It's only x values. So the amplitude of 1, sorry, the maximum of 1 and the minimum of -1 will stay the same. So let's see. If I go to 1/2, there's 1/2, so it stretches it out. Ooh, let me go exactly 1/2. There we go. And you can see that starts from 0, ends at 4 pi. So the period doubled. Okay, so let me return this to 1. And so what we saw there, let me just for comparison, that's what happened. Okay, so overlaid with the original graph. The next one, y equals 3, y equals sine of 3x. Well, now the b value is 3. So what happens when the b value is 3? That's 2 pi divided by the absolute value of b. That's 2/3 pi. So you should see the period of this new function with a b value of 3, the period should be 2 pi over 3. So let's see what happens. So if I go turn this on, 2 pi over 3, let's turn all this off so it doesn't look as messy. So there we go. That's a period of 2 pi over 3. If I start from 0, 0, 0, and just looking at the x value, I go pi over 3, and then there's my 2 pi over 3 for a b value of 3. Okay, so let's turn on all of that. That's the original function, sine of 1/2 x. sine of 3x. All right, everyone, let's put it all together. Everything, integrated examples here. State the amplitude and period of each graph below. Okay, amplitude. That is simply the max minus the min divided by 2. So that is, the max value is 2, min value is -2, about the horizontal central axis, right? So the horizontal central axis, okay, the amplitude is the maximum vertical distance the graph of a sinusoidal function varies above and below the horizontal central axis of the curve. So that is 2 minus -2 divided by 2. That's 2 plus 2 is 4 divided by 2 is 2. So an amplitude of 2. And the period, let's sketch this out. The period, if I start at, let's say, this point, let's do one full cycle. So this is a half cycle. And then, oops. Sometimes doing this period is a bit tricky here. I'm going to start with some place that doesn't require me to do a whole ton of math here. If I start here, so I'm going to go here. If I start here, I'm going to go, that's a half cycle. And then I'm going to go a full cycle here. So what is that distance? That's pi over 2. So pi over 2 is right there. Okay, so each tick mark is pi over 6, 2 pi over 6, 3 pi over 6. So this is 3 pi over 6 if I'm reading the graph, which is pi over 2. So my period is 0 to pi over 2. So my period is pi over 2. Okay, what about my amplitude? Let's go amplitude and period of the second graph. Okay, this is the horizontal central axis. So the amplitude, I'm only shown half of the cycle. Okay, so my amplitude is 1.5 minus -1.5 divided by 2, and that is positive 1.5. Okay, because I know the rest of the cycle would just be a mirror image in below the x-axis for the second half. Okay, so what about the period? What is shown here is half a period, folks. So this is half a period. So half of a period is shown. Half of a period is shown. So a full period equals, that's 3 pi for the half period. 3 pi times 2 equals 6 pi. So a full period is 6 pi. All right, folks. Let's do an integrated example. Okay, sketch the graph of y equals -3 cosine of 2x for at least 2 cycles. So what I'm going to do is I'm going to graph the base function y equals cosine of x and then develop the transformation from there. Yep. Okay, so in black, I'm going to do y equals cosine of x. So giving you the handy little chart here. So for at least 2 cycles. So when we graph the cosine function, I'm going to give you all the values here. So that's 1. That's square root of 3 over 2. That's 1/2. 0, negative 1/2. Negative square root of 3 over 2. Negative 1. Negative square root of 3 over 2. Negative 1/2. Remember, these are all values from unit circle, right? So you should know these by now. 1/2, square root of 3 over 2, and 1. Okay, so when I graph this in black, here's the trick with the cosine function. I'm going to plot the quadrantal angles. Okay, so if I plot the quadrantal angles at 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and 2 pi 1. Okay, and then also pi over 3, 1/2. So pi over 3, pi over 3, 1/2. Right, so I'll plot those in. Okay, and I know it continues like this, right? So let's use our properties of symmetry here. Okay, and I know 3 pi over 2 is roughly about there, right? So this is how I quickly and neatly graph a cosine function. Okay, let's, nice smooth curve. Okay, there we go. All right, so SRT, or I'm going to do the reflection first. So I see that there's a reflection in the x-axis because I have an a value less than 1, right? So I have an a value less than 1, right? So I'm going to reflect the cosine graph in the x-axis, sorry. So I'll put some dots here. Okay, and I'm just doing a reflection, folks. Okay, there we go. Right, and I'm going to draw a dotted line here. Look at that magic dotted line. So this is, and let me do my legend or key here. So this, I'm just going to make some room up here, folks. Sorry about that. For my key. Oops. What can I make some room here? Let's do this. I'm going to have to carve out some real estate here. Alright, so this will be y equals cosine of x. This would be y equals negative cosine of x. Okay, the dotted line. Okay, and let's continue. So let's do the, in blue, I'm going to show the vertical stretch about the x-axis by a factor of 3. Okay, so that is the 3 here. So absolute value of a equals 3. So I'm going to show that vertical stretch, folks. All right, so let's go ahead and do that one. Okay, so all the x values, remember this is off of the dotted line graph, right? So 1, 2, 3. Okay, 1, 1, 2, 3. Okay, x-intercepts don't change. Okay, 1, 1, 2, 3, and then 1, 1, 2, 3. I'm doing some of the easier ones to read because I don't want to mess up the transformation here, right? So 1, 1, 2, 3, and then 1, 1, 2, 3, and then here x-intercepts are the same. 1, 1, 2, 3, 1, 1, 2, 3. Okay, and so on. 3, 1, 1, 2, 3. Okay. And so what does this look like? Okay, and I should mention that this continues on, right? So I forgot to draw some arrows here. Okay, likewise with this one, I forgot to draw arrows. That continues on, and that continues on, and that continues on, and that continues on. Okay, so blue. So my graph in blue, oops, that is y equals -3 cosine of x. Okay, one more transformation to go. That's a b value of 2. So the b value of 2, just do it off to the side in red. So if b equals 2, sorry, I'll do it over here. So for a b value equal to 2, right, that is a factor of 1 over absolute value of 2. So that's a factor of 1/2. So all the x values from the blue graph get multiplied by 1/2. So this is what happens. So okay, so one half, right? So on a horizontal stretch about the y-axis, the y values don't change. Now it's the x values. So from the blue graph, I'm going to go exactly 1/2 of all these points. So right there, this one goes out here. Okay, let me just get rid of that. So this one goes out here. Okay, and then like that. Okay, halfway. And then this one, halfway would be right about here. Okay, and then by now you should see some symmetry going on where I can start plotting these in a symmetrical way to make my work faster. Okay, and you get the idea. Okay, and then let's draw a nice smooth graph. Okay, I'm gonna mind my arrows there. Okay, and just smooth as you can. Close enough. Okay. All right. So this one would be the final version. Y equals -3 cosine of 2x. Okay. Let me give you you can do this on your graphing calculator. The x values will be 0, 4 pi, pi over 6, and the y values would be -3, +3, and 0.5. And remember, radian mode when you are plotting these, okay? Radian mode. Okay, let's state our domain. State the following characteristics as an exact value in radian measure where x is defined on the set of real numbers and is expressed in radians. This is for just one of the graphs, the final transform graph, -3 cosine of 2x. So the domain clearly on all the set of all real numbers, domain is -infinity to +infinity. The range is a low of -3 and a high of 3, okay, with square brackets. Maximum, that's read from the graph. Remember, the horizontal central axis is, let me just highlight that. This will be important later when we do translations. But there's my horizontal central axis. Maximum value is 3. Minimum value is -3. Amplitude, so it's 3 minus -3 divided by 2, and that is 3. So my amplitude for the red function, so if I start from the horizontal central axis and I go all the way up, it's 3, a value of 3. Okay. Next one, period. Remember, it's defined by 2 pi over the absolute value of b. Well, that's 2 pi over 2, and that equals pi. Well, is the period pi? Let's take a look. Take a look at the graph. So in green. So if I start at, let's start at pi over 2. Yeah, something easy to read. Pi over 2. So I'm going right there. That's a half cycle. And then I'm going to go up all the way up for a full cycle, returning peak to peak. Okay, so I start and I return at the same spot. Okay, x value wise, and that's pi over 2 to 3 pi over 2. Okay, is that a period of pi over 2? Well, is that a period of pi? So if I start at pi over 2, so this is for my period, folks. If I start at pi over 2 and I end at 3 pi over 2, so what's 3 pi over 2 minus pi over 2? That is 2 pi over 2, or pi over 2 for our period. Okay, x-intercepts. This is the way I look at it. The x-intercept is right here. That's pi over 4, folks. Okay, pi over 4. So let me highlight that in another color. Let's do pink here. So that's the x-intercept, pi over 4, but it occurs every how many units? Right here. How many units? That's in the positive direction, so it must go in the negative direction as well. Well, how many units does it go? If you read the graph carefully, every pi over 4 units, or it starts at pi over 4, it actually, the x-intercept occurs every pi over 2 units. So look at the spacing between each of these. This is pi over 2 units. Okay, so pi over 2 units. So how do we write that in general form here? So if I start at pi over 4, I'm going to add pi over 2 units, but I multiply by n, and then I say n is an element of integers. So if n equals 1, if n equals 1, then pi over 4 plus pi over 2 times 1. Okay, that's 3 pi over 4. Well, is that our next x-intercept? Yep, right here. That's 3 pi over 4. Okay, and then you can keep going, n equals 2, and then you can even try n equals -1. Okay, n equals 0 would just give you pi over 4. Okay, so this is our general format for the x-intercept. And then the y-intercept is just -3. You can clearly read that from the graph. Okay, let's do the number 2 in the putting it together section. So putting it together, let's do a stretch. Two kinds of stretches: a vertical stretch, a horizontal stretch, and a reflection. Okay, so let's take a look. So first of all, we're starting with the cosine function, y equals cosine of x. There it is. Okay, and then the first thing I'm going to do is reflect it in the x-axis. Sorry, I'm going to reflect it. Yes, if we're going to reflect it in the x-axis with an a value of -1. So if I'm going to just overlay it like this, right? So if I start here, so here's my cosine function. I'm going to overlay the dotted line as the cosine function. And there it is, right? So when I do a value of -1, you should see a reflection in the x-axis. So it's a vertical, it's a reflection in the x-axis. So look where the maximums are, look where the minimums are, and you should see them swap positions. So let's go to -1. And indeed, if I put the original function back, they indeed swap positions. Okay, so let's leave it at a equals -1. So we're at y equals negative cosine of x. The next thing to do is I'm going to go y equals -3 cosine of x, right? So -3 cosine of x is an a value of -3. So if I turn this on, we should expect all the peaks and troughs to elongate in the vertical direction by a factor of 3. So if I go -3, that's what it's going to look like. Okay, so let's return to -1, and I'm going to overlay that. So that's what we went to, right? So we grew all the way to a equals -3. Okay, so let's go back to -1. I want to turn this off. And then the last part is a b value of 2, right? So we have y equals -3 cosine of 2x. A b value of 2 means a horizontal stretch factor about the y-axis by a factor of 1/2, right? So 1 over absolute value of b. Okay, so we should expect like a spring compressing. We should see the maximums and the minimums come together and compress. So if I do that, let's take a look. And in fact, it does. So if I look at this point right here, that's pi 3. Well, what's this point right here? Pi over 2. So the x value was multiplied by a factor of 1/2. So let's go back, and I'm going to turn that on. So we start with y equals cosine of x. Then we reflected it in the x-axis. There it is. And then we stretched it vertically about the x-axis by factor 3. There it is. And then we stretched it horizontally by a factor of 1/2. That's a b value of 2, which is a factor of 1/2 about the y-axis. So like a compressing spring, the final form in red. Okay. And then let me just turn off the other ones, and that's the final transformation.